An ideal gas is a model. It helps us imagine how gas particles behave in the simplest possible way. In an ideal gas, the particles move quickly and randomly. They are so small that their own volume is treated as almost zero. There are no attractive forces between them, and when they collide, the collisions are perfectly elastic. That means no energy is lost during collisions. A real gas is a little different. Real gas particles do have volume, and weak attractions can exist between them. Because of that, real gases do not behave perfectly like ideal gases all the time. At high temperature and low pressure, real gases behave much more like ideal gases. But at low temperature and high pressure, the differences become much more noticeable. Why does that happen? At low temperature, particles move more slowly, so the attractive forces between them matter more. At high pressure, the particles are pushed closer together, so their own volume can no longer be ignored. So the key idea is simple. Ideal gases are a useful model, but real gases can deviate from that model, especially at low temperature and high pressure. This picture shows how pressure, volume, and temperature are related for a fixed amount of gas. First, at constant temperature, pressure is inversely proportional to volume. So when volume goes down, pressure goes up. That happens because the particles have less space, so they collide with the container walls more often. Next, at constant pressure, volume is directly proportional to temperature. As temperature increases, particles move faster. To keep the pressure the same, the gas expands, so the volume increases. Then, at constant volume, pressure is directly proportional to temperature. When temperature rises, the particles move faster and hit the walls harder and more often. Since the volume cannot change, the pressure increases. The graphs show these relationships clearly. Pressure and volume form a curved inverse relationship, but volume and temperature, and pressure and temperature both form straight line relationships. One more important point is absolute zero. If you extend the temperature graphs backward, they point towards 0 Kelvin, which is minus 273 degrees Celsius. So in short, decreasing volume raises pressure, increasing temperature raises volume at constant pressure, and increasing temperature raises pressure at constant volume. All of these gas relationships can be combined into one important equation. PV equals nRT. Here, P stands for pressure, V stands for volume, N is the number of moles, R is the gas constant, and T is temperature in Kelvin. That last part is very important. For gas equations, temperature must always be in Kelvin, not degrees Celsius. This image also shows Avogadro's idea. At the same temperature and pressure, equal volumes of gases contain equal numbers of molecules. So even if the gases are different, equal volumes under the same conditions contain the same number of particles. Now let's look at molar volume at STP. STP means standard temperature and pressure, which is 273 Kelvin and 100 kilopascals. At STP, 1 mole of any gas occupies 22.7 cubic decimeters. At the bottom, we also have the combined gas law. For the same sample of gas, P1V1 over T1 equals P2V2 over T2. This equation is useful when the conditions of a gas change from one state to another. It lets us compare pressure, volume, and temperature before and after the change. So the big picture is this. PV equals nRT connects all the main variables, Avogadro explains equal volumes, and molar volume gives us a useful value at STP.